So what we're going to do now is we're going to continue our coverage of patterns, picking up from where we left off last time by focusing now on the active object pattern. And you'll see that this pattern is a pattern that appeared in the Post-it 2 book, as well as you can find it on Wikipedia. There's a Wikipedia page about it, and there's also a link, I think, from that Wikipedia page to an article that I wrote many years ago that talks about this pattern as well. Here's the Wikipedia link. You can find it there. You know that you've made the big time when someone writes a Wikipedia link about something you've written a paper on. So let's give a context for this pattern. So the context we're going to focus on in this video will be Android clients that want to access or manipulate objects that are running in a different thread of control. So imagine, for example, we've got our environment where we've got a background thread that's doing some work and it wants to send some information, a message, for example, from the background thread to the user interface thread to tell it to do something. So in this context, a client is anything that invokes an object's methods. So it oftentimes in client-server programming, the client will be a computer that's different from the server computer, but that doesn't necessarily have to be the case. In this particular use case, it's just somebody who's invoking a method on an object that will run in a different thread of control. So again, here's the scenario. We have a background thread that's going to invoke the send message method on a handler, and that handler will be associated with the user interface thread. So it'll actually reside in the user interface thread. More generally, it doesn't have to be a background thread talking to the user interface thread. It could be any threads that interact by having messages passed from one thread to another thread via a handler. So what's the problem here? Well, what we'd like to be able to do is make communication between threads as transparent as possible so that you don't have to stop and think about the hardware issues. You don't have to stop and think about the software infrastructure issues. You don't have to think about synchronization. You don't have to think about moving messages between threads. All those kinds of things are going to be shielded from your knowledge. And another thing we want to do here is we want to be able to make sure that the processing of methods that are computationally intensive or processing intensive that are invoked in an object don't block the entire process, and in particular don't have to block the calling thread. We want to be able to have things running concurrently so that you can have an overlap between computation and communication. Another thing that we're trying to do here, another problem we're trying to solve, is trying to simplify the programming of synchronized access to shared objects. So rather than having to put locks in our code explicitly, we're going to use some other means in order to be able to provide boundaries of concurrency. And as before, as is often the case, we want to make the method call be the boundary of concurrency, which is something that's actually you're familiar with in the context of the monitor object pattern that we've talked about earlier. So what's the solution in this case? Well, what we're going to do is we're going to apply the so-called active object pattern, which is this Post-it 2 pattern that is used to decouple method invocation on an object, which occurs in one thread, from method execution, which occurs in another. And you can kind of see that in the diagram below. You have one thread that's invoking a method on an object in one thread, that's the client. And then we have a different thread that's actually performing the operation, and it's distinct from the calling thread, the client thread. So again, take a look at the Wikipedia link for a bit more information and some pointers to other resources about this pattern. So the key goal here is, as shown in this diagram, is that method invocation should occur in the context of the client's thread of control. You can see the red thread icon in the left-hand side of the diagram. And then method execution will be occurring in a separate thread of control, in basically the server thread. I'm using that word server loosely here because it doesn't have to be a separate server. It could be the same process, just in a different thread of control. From the client's point of view, however, it thinks it's just invoking an ordinary method. It just thinks it's saying, hey, send this message or send these parameters from my thread context to a different thread context where they're executed. And in particular, what that means is that the client should not manipulate any synchronization mechanisms, any reentrant locks, any semaphores, any synchronized statements, synchronized methods. All those things should be completely shielded from it. It shouldn't have to know anything about the way in which the communication is taking place. And that's actually also true of the server as well. So now let's go ahead and talk about the intent and the applicability of this pattern as described in the POSA 2 book. So the intent of this pattern is to define service requests on components or on objects and make these service requests the units of concurrency. So that's what we're doing. We're sending requests that will be running concurrently. And then these requests for the service will run on the component in a different thread, or could be different threads, depending on how you implement the active object as one thread or a pool of threads that is different from the requesting client thread. So the key point here is client invokes in one thread, and then the implementation runs the request in a different thread of control. Why is this a win? Because it enables the client and the component to interact asynchronously in order to produce and consume the results of making these invocations on the service that the component provides. So what are the circumstances under which it makes sense to consider applying this pattern? Well, one situation is when you want the methods in an object's interface to define its concurrency boundaries. This again should sound very familiar. This is pretty much the same thing that the monitor object pattern is doing. You also want to make the objects themselves be responsible for synchronizing a method call and also scheduling the method call transparently without requiring any interaction or any explicit intervention from the client. Leave it to the object implementation or the component implementation to do the actual synchronization and scheduling. Another big motivation, and this is now what's going to start to differentiate this pattern from the monitor object pattern, we want to allow the methods, the object's methods, to block for a long time during the execution, but we don't want to block the client. And then, of course, another goal here that makes this pattern useful is when you want to have multiple requests from multiple clients, potentially all in multiple threads, running concurrently on an object at the same time. Now, this can be a great way to scale things up transparently, but you have to be careful because there could be some issues with respect to synchronization of the object's shared state, where the shared state is shared between different threads that are executing internally to it. But again, that's the object implementation's problem, not the client's problem. And then another motivation for using this pattern, which, as it'll turn out, is also potentially a liability, is if you want the invocation order to be independent of the order in which the methods actually execute. So if you don't really care what order the methods execute that are invoked by clients, either by the same client in one thread or multiple clients in multiple threads, if you don't really care what order they run in, if you just want the results back whenever they're done, then this pattern can also provide a tremendous amount of useful non-determinism because you're just letting things run and they finish whenever they finish. Now, it's worth noting the similarity here between some of these applicability dimensions for the active object and comparing and contrasting how they relate to the monitor object. So if you take a look here, you can see that the first couple of applicability dimensions, having the methods be the concurrency boundaries, making the object implementation responsible for synchronization and scheduling, that's really sort of the same thing that we have with the monitor object pattern. But the other characteristics, like blocking for a long time and letting things run in different orders, wildly different orders, and then allowing multiple client requests simultaneously running concurrently, those are ways in which the monitor object and active object patterns differentiate from each other. So now that you have a little bit of an understanding of the intent and the applicability of this pattern, let's talk about the structure of the active object pattern. And it's actually got a fair number of pieces, although when you break it down, you see it's really not all that complicated. But there are a number of pieces. And the reason for all the pieces is to try to make this look as much like making method calls on objects as we can possibly do while still providing all those nice concurrency features. So we'll start off by talking about the proxy that's the interface that the client sees. And a good example in the mapping to the Android context would be invoking the send message call on a handler where the handler is intended to run in a different thread of control. So that's the proxy. Send message method call is the proxy. And there's another thing that's called the future. This is itself its own pattern. And the future is what's returned when you invoke a method on a proxy. So if you invoke a method on a proxy, you get back a future. And that can be used to reclaim the results when they finish. So in this case, that could be the handler. The next element that we're talking about here is the method request. And the method request is what the proxy converts the method call into. So when you invoke a method call on a proxy, it converts the parameters and it sticks it into a message, which is termed the method request in the context of the active object pattern. In our particular case, that's the message itself. And then that message is passed off to another thread of control, and it's stored in something called the activation list. And these are going to be the list of all the method requests that are pending processing inside the context of the active object in a different thread of control. So in this particular case, that would be the Android message queue class. Then there's something called the scheduler, and the scheduler is what's used by the active object implementation to decide which of the messages or method requests that are queued up in the activation list should be run next. So in this particular case, that's handled by the Android feature called the looper. We talked about looper before. We talked about the command processor pattern. And then there's another role here called the servant, and the servant is what is used to actually implement the active object's capabilities. So that's what is the target of callbacks. And then essentially what happens is that the scheduler is going to be used to convert the method request back into a method invocation on the corresponding method that's provided by the servant. So in this case, it would be whatever we implement, my handler or some implementation that's going to do the right thing based on the messages that are passed to it. Then we have a client. Client, of course, is what's going to actually use the proxy in order to make method calls that will then be run in a different thread of control. So the client runs in a different thread of control than the scheduler and the activation list and the servant and so on. And the method request is how the information is passed from client to the active object implementation. And the future is what comes back to let the client retrieve the results if it's a two-way call. So in this case, the client would be some Android activity. Okay, so now that you know a bit about the participants in the pattern, let's talk about their dynamic interactions. And again, this diagram looks a little daunting at first, but it's really not that scary when you break down and see what's happening. So the client invokes a method call on the proxy. The proxy will convert the method call into a message request, passing that method request to the scheduler, and then it returns a future back to the client. So that's how the client can know when the request is done if it's a two-way call. The scheduler will go ahead and enqueue the method request in the activation list. And then at some point later, because of course it's got its own thread of control or threads of control, there will be a way for the scheduler to dequeue method requests in the right order at the right time under the right conditions, and then invoke the method request by converting it back into a method call on the servant that runs in a separate thread of control from the point of view of the caller, from the client. And the clients, if it's in fact an asynchronous two-way call, then clients can get results from the invocation by using the future and either poll it or by having some kind of callback used to dispatch it through some kind of callback mechanism. And there are different ways to do that. So let's talk a bit about the pros and the cons of this particular pattern. So one of the nice things about this pattern is it helps to enhance concurrency, and it simplifies the complexity of synchronization because it shields the client from all those details. And really, it shields the object implementation from the bulk of those details unless the object implementation needs to synchronize active object implementation state if for some reason they're shared fields or shared objects within the context of the active object. So client threads And asynchronous method invocations can run concurrently. Those things are running in different threads of control, just like having a background thread that's passing a message to the user interface thread. Those can run in different threads. The scheduler can take into account various synchronization constraints or other conditions or expressions that are needed to serialize access to servants so that they run at the right time, under the right conditions, perhaps in the right order. You can also transparently leverage the available parallelism. So you can have a whole bunch of different threads that are sending requests. You can have a whole bunch of threads that are handling the requests. Those things can run concurrently, thereby taking better advantage of modern multi-core processors, for example, or even if you use the active object in a distributed system, you can have different computers involved. And therefore, actually, multiple methods can be running on the same active object if the scheduler is configured to use a thread pool. And of course, if the underlying operating system and hardware allow concurrent and parallel execution, which almost everything today does. Another interesting consequence, which we'll see as both a pro and a con, is that the method execution order, that is the order in which the active object implementation will run method calls on servants, could in fact be different from the invocation order that the clients make. So these don't have to go in lockstep. They could be delayed in time. They could be delayed just because one thing takes longer to run. And you can actually have the scheduler be aware of synchronization constraints that are defined based on the scheduler and its scheduling policies and any guards that are used to make sure that things run at the right time, the right order, and so on. As always, not everything is hunky-dory, not everything is rainbows and unicorns, so there are some downsides, some limitations to this pattern. One potential limitation, and of course this is all relative to various things, is there may be some higher runtime overhead, and this runtime overhead is going to be incurred because of just the properties of concurrent programming. When you start passing information from one thread to another, there's going to be more synchronization and locking overhead. There will likely be context switching overhead. There will likely be data movement and memory management overhead. And you just have to make sure that the operations you're running in parallel or concurrently in a pool of threads, for example, in the active object implementation, is worth it relative to the overhead of doing context switching and synchronization and memory management and data movement. So you just have to benchmark your code and make sure it's going to actually help give you an improvement. So here's some of the things where this runtime overhead could be incurred. So you have to allocate messages dynamically because you want to pass them from one thread to another, and you want to have one thread allocate them and one thread free them up somehow. So that takes more overhead. You need to be able to have synchronization occurring when you pass things from the calling thread and stick it into a message queue, which is typically implemented using a technique like the condition object and the say linked blocking queue or the array blocking queue that you get with Java util concurrent. So there's synchronization overhead there. There's also context switches, which is involved when you move a context from the caller to the server or to the implementation, and that involves putting one thread to sleep, waking another thread up. And then there's, of course, updates in the CPU cache. The cores may be updated and you have to move data from one core to a next. These are not the end of the world issues. They're just typical overheads for concurrency. But if the operations you're doing are very short-lived, like you're going to add two numbers together, it's really not worth the overhead of doing an active object. So make sure that the computations run for a while to make it worthwhile. Another potential downside is complicated debugging. So anytime you start having concurrent programming, it's typically more complicated to debug your code. And that has to do really with the underlying non-determinism of the schedulers that are used to schedule the method requests to run on the servants in one or more threads in the active object implementation. And there's nothing inherently wrong about that. It just, when you have concurrency, it's more complicated. So let's talk about some of the known uses of active object pattern in practice. So there's actually a whole family of languages and libraries that implement a formalism called the actor model. And this is a mathematical model of concurrent computation that treats actors or active objects as the universal primitives of concurrent digital computation. And there's a bunch of languages that support the actor model, Scala being one. There's something called Erlang or Erlang, something called Salsa. So you can read more about the actor model at this Wikipedia link. And an actor model is basically a bunch of active objects. If you have an active object and it receives a message, then the actor or the active object implementation can make decisions based on that. It could create more actors, send more messages to other things, so you can kind of distribute out the load. It can determine how to respond to the next message it receives. And it can do this in a very clean and easy to reason about formal way. Various languages and libraries provide support for implementing active objects. So with C++11, you can implement active objects using a technique like what I show here. If you want to learn more about this particular example, take a look at the link at the bottom of the slide. But basically, it's creating an active object that has a message queue. And when you send a message, as you can see here, it's going to enqueue the message onto the message queue. And then you can see that when the constructor is run, it's going to go ahead and create a new thread that calls the run method. And the run hook method just waits until the object goes away, and it pulls the messages off the queue and it executes them. So a very simple example, not necessarily the world's most profound example of active object in C++, but it's very concise and gets the point across. I developed a framework for doing active objects. It was called the ACE task framework. You can read more about that at the link below. And it implements a subset of the active object pattern and makes it very simple to implement active objects. You can actually look at the Java Executor Service framework as implementing a variant of active objects as well. So when you submit tasks that are callable tasks, then those can be implemented using active objects. And when you make the submit call, you get back a future, and everything maps really nicely onto the various roles and responsibilities in the active object pattern. Something that we've been talking about here as our motivating example, of course, is the Android Hammer framework, where you can have, say, a background thread making a method invocation, which is sent to the user interface thread, or you can just have threads pass messages back and forth without distinction whether one is the user interface thread or not. So this is a really good canonical example of a subset of the active object pattern that's used in Android. So to wrap up the overview, it's often the case that clients want to be able to issue requests on components or make method calls on components without blocking until those requests finish executing. You don't have to wait for them to finish. You can do other things and then get the results back through a proxy. You'd also like to be able to make it possible to schedule the requests so they run at the right order or at the right priority or so on. And to do this, the active object pattern is a nice way to keep track of all the requests, and mapping it onto the various roles and responsibilities in the pattern makes it easy and convenient to write these kinds of concurrent actor-oriented models, where the concurrency and synchronization is pretty much transparent to clients and to the implementation of the components themselves. Take a look here if you want to see an earlier version of the active object pattern description, which was then improved in the Post-it 2 book. It's really worth taking a look at active object and comparing it to monitor object. They're very similar in a lot of ways, but active object is going to give you more concurrency, whereas monitor object is going to give you less flexibility, but probably also incur less overhead too. So as a general rule of thumb, active object is more powerful, but it's also more complicated to implement, not really more complicated to use, and potentially has a bit higher overhead because there's more context switching and more ceremony going into an active object than going into the monitor object. But again, these are really nice patterns to understand and then be able to compare and contrast which ones to use under different circumstances. And you can actually take a look at this paper here, or at the Post-it 2 book for that matter, to find a comparison and a contrast between active object and monitor object. So that's the end of part 1 of our discussion of the active object pattern. What we'll do now is we'll talk about how you can implement this pattern, or how this pattern is implemented in the context of the Android Hammer framework.